Hi, today I'm going to be talking about the Comet 67P and the Rosetta Mission 267P, which was the first ever mission in which a spacecraft went into orbit around a comet. So first I'm going to give you a brief overview about the Rosetta mission, and then I'll give you some general characteristics about the comet itself before plunging into the chemistry and talking about some of the findings from the Rosetta mission, as well as some of the new questions that are being raised. First up, a brief overview of the mission. The Rosetta mission broadly was to catch Comet 67P and accompany it into the interior solar system. So not only was this the first time that a spacecraft was going to go into orbit around a comet, but this was going to be the first time that a spacecraft was going to be able to observe directly how a comet changes as it receives more and more warmth from the sun as it gets closer to the sun. So this mission was remarkable in that regard. And specifically, the name of this mission comes from the Rosetta Stone, which is a stone tablet that was found in Egypt near Rosetta. And on this tablet, you have two types of ancient Egyptian writing. Then you also have some Greek. That coupled with the Philae obelisk, which also had hieroglyphs and Greek writing on it, was used to decode Egyptian hieroglyphs. And this was really important in unlocking some of our understanding of ancient Egypt. So it's appropriate that the Rosetta mission was named such. So the spacecraft itself was called Rosetta, and then it had a lander called Philae. And together, Rosetta and Philae were used to decode 67P. And understanding comets like 67P are important for unlocking our understanding of the early solar system, and even as far back as the molecular clouds from which planetary systems are formed. So this is an appropriate name in trying to figure out our ancient history with respect to the wider solar system. So the Rosetta mission consisted of the orbiter itself, or Rosetta, and Rosetta had numerous instruments, including mass spectrometers and spectroscopy instruments to study the nucleus of the comet itself, gas and particles that were being emitted from that nucleus, and then also how the nucleus interacted with solar wind. And then the Philae lander was sent to study the cometary nucleus in a qualitative and up close sense relative to the Rosetta orbiter itself, but also to study the cometary surface and take samples of the cometary surface. So the Rosetta mission was about a 12-and-a-half-year mission. Rosetta was approved in November 1993, but it didn't launch until 2004. And it took Rosetta 10 years to catch up with 67P. Once it reached 67P in 2014, it went into orbit around 67P and studied the comet up close for a little over 2 years before plunging into the surface of 67P. In 2014, shortly after Rosetta arrived at 67P, it launched the Philae lander. And at best, if Philae did successfully land on the surface of the comet, it would collect 3 to 5 months worth of data, and it had solar panels on it so that it could recharge and continue collecting data. So Philae almost didn't land on 67P. It bounced twice before landing, and on one of the bounces, had Philae been going about 4 centimeters per second faster, it would have escaped the gravitational pull of the comet. So it just made it. But of course, when it landed in the shadow of a cliff. So there wasn't adequate sunlight to recharge the battery, which could only last for about 60 hours. So Philae took 2 days worth of data before going into hibernation mode, and then occasionally, as it slowly charged up its battery, it would send data back to Rosetta. But one problem with it being in the shadow of a cliff was that Rosetta couldn't actually see where Philae was, and knowing where Philae was important for putting the data from Philae into context. So when Rosetta was ending the orbit and getting ready to plunge into the surface of the comet, it did catch a glimpse of Philae, so was able to put that data into context, and it wasn't a complete failure, but it was a close shave. So now I'm going to talk about the comet. 67P is really interesting. It was first observed in 1969. And one thing that's really interesting and peculiar about 67P is that if you read any headlines about it, you'll see that it's duck-shaped. And if we look at a picture of 67P and superimpose a rubber ducky onto it, we see that, yeah, it does kind of look like a rubber duck. So that's something that makes the 67P extra special. So naturally, when I was looking for information to put in this presentation, I went to Twitter. And 67P is on Twitter, so I tweeted at them, and I asked what was one thing that they wished everyone knew about them. And they responded, and it was not disappointing. Comet 67P tweeted, "A human is asking what one thing I want the world to know about me. Well, it's easy. Because I'm 4.5 billion years old and older than birds, ducks are Comet 67P shaped, not the other way around." So if there's one thing that you take away from this talk, I hope it's that ducks are Comet 67P shaped and 67P is 67P shaped. So this big duck or 67P shaped hunk of ice is like any other comet, basically a big snowball. So it's mostly water. And it really is big. So this is what 67P would look like over Los Angeles. And the reason for the duck shape is that 67P has two lobes, the largest of which is 4.2 kilometers in diameter. So really isn't that remarkable in size compared to other comets, but by our standards, it's pretty big. There are various features across the surface of 67P, including pits, and these pits allow us to look directly into the nucleus. We also have cliffs that range anywhere from 100 meters to 1 kilometer in height. There are also boulders, so occasionally you have these isolated boulders which are 25 meters across, but quite often the boulders are in fields, as you can see in the right patch of boulders. There's also plenty of smooth patches, and then there's rougher areas of layering, and these layers extend as deep as 650 meters, and theoretically they allow us to study how the comet has changed over time. 67P on top of all that ice is a thin consolidated surface, so you can think of it having somewhat like a crust that you would see on a loaf of bread. It has a mass about 100 million times that of the International Space Station, and then it has a density about that of cork or wood. And then 67P is also a Jupiter family comet. So as you can see on this picture of the orbit of 67P, which is in red here, its orbit extends just past Jupiter at the aphelion, or the farthest distance from the Sun, which is 5.7 AU, and then at its closest approach to the Sun, or perihelion, 67P is just outside Earth's orbit at 1.2 AU, where 1 AU is the distance between Earth and the Sun. And it being a Jupiter family comet, it has a pretty short orbital period of about 6.5 years. And this is the whole reason why the Rosetta mission was possible. It having such a short orbital period made it feasible for scientists to accurately project how long it would take an orbiter to get to 67P and accurately map what that flight path would look like. So because of the short orbital period, you're able to study directly how the comet changes as it approaches the sun, and directly study like the coma, which you can see, and the fuzziness that's being emitted from the comet. So really, really exciting. So now I'm going to go into the chemistry, and specifically I'm going to focus on water and organic molecules. So one thing that was studied was the D to H ratio in water, so D meaning deuterium and H meaning hydrogen. So in water, you can have what's called heavy water, which is instead of H2O, or two hydrogens and an oxygen, you have HDO, which is a hydrogen, a deuterium, which is just heavy hydrogen, and an oxygen. So the D to H ratio on Earth is shown by the dark blue line, and you can see that other Jupiter family comets, shown by the dark green circles to the right, have a D to H ratio that's very similar to Earth, but 67P, even though it is a Jupiter family comet, does not match that D to H ratio. So in fact, it has a D to H ratio that's about 4 times that of Earth. So this raises a couple questions. One is that maybe Jupiter family comets have completely different origins, and maybe 67P isn't a Jupiter family comet at all. In fact, it might be a Kuiper Belt object. Another idea that came from this is that Earth's oceans, which have previously been thought to be populated with water from comets, might come from asteroids instead, that maybe the D to H ratio is too high in comets. But of course we have a small sample set, and we don't really know for sure. And then if we look at the organics, so I have water, carbon monoxide, methane, and ammonia listed, and these are parent molecules for a complex organic chemistry in 67P. And the ammonia, which is shown in red, is the only one of these that was not definitively detected. But as I'll show you in a moment, we have strong reason to believe that ammonia would in fact be on 67P because there are lots of nitrogen-bearing complex organics. So it's no surprise that that water generally dominates, but in some regions you have an excess of carbon monoxide and carbon dioxide. So this is uncharacteristic for a Jupiter family comet. But regardless of the relative abundances of water and other molecules, these parent species can form different daughter species. So alcohols and carbonyls are formed from water and carbon monoxide. Amines and nitriles are formed from methane and ammonia. And then the amides and the isocyanates are formed from all of these. And in 67P, we see a variety of each of these daughter species. So the 4 that are shown in green are ones that are that were discovered for the first time in a comet with 67P. And now I want to draw your attention specifically to methylamine and ethylamine, which are now shown in the light green box. And these two molecules are related to each other, but they're also related to glycine, specifically in that methylamine is formed from the hydrogenation, or the addition of H2 to methanamine. But methanamine has another product, and that is alpha aminoacetonitrile. And that molecule is a direct precursor of glycine, or is thought to be in the interstellar medium if it would form there. So this has strong potential for there being prebiotic or pre-life molecules. And in fact, we do see glycine, or the simplest amino acid. So glycine has already been detected in another comet called VIL2, but the the presence of glycine is kind of like the holy grail for cosmic chemistry. So the fact that there are two instances of this being in comets really strengthens this idea. So that's really exciting. And then another exciting thing doesn't have to do with organic chemistry directly, but it's the presence of phosphorus. So phosphorus is a key element in the energy that fuels life, and it's never been detected in a comet before. So this is another first, which is quite exciting. And then another thing that I haven't mentioned is that there is sulfur chemistry. So essentially in 67P you have all the ingredients for life. So again, going back to the carbon monoxide and carbon dioxide being or having higher abundances than other Jupiter family comets, perhaps that's evidence that 67P isn't really a Jupiter family comet at all. But what's even more exciting about the organic chemistry is that there's evidence that supports the idea that comets delivered prebiotic molecules to Earth. But to summarize, 67P gave us very few answers and a lot more questions than what was started out with the mission. The first question is whether 67P is a Jupiter family comet at all. Perhaps it's a Kuiper Belt object. It has a higher D to H ratio than is typical for the Jupiter family comets, and the same can be said for the carbon monoxide and carbon dioxide abundances. So perhaps 67P was actually adopted by the Jupiter family comets after it migrated inwards. But with the high D to H ratio in water, this goes against the idea that comets delivered water to Earth. So we have to look elsewhere for the source of Earth's water, probably to meteorites and asteroids. And then finally, the presence of cometary glycine and then SNOPs, or carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which are the basic ingredients for life as we know it, supports the idea of perhaps pseudopanspermia, or the delivery of the building blocks of life via comets and asteroids to an early Earth. And if that's the case, maybe comets are like DHL trucks in space, where DHL is delivering the heralds of life. Thank you for listening.